You might have come across these scenarios where some methods just don't make sense in the given context. For example, some SMS notification class extending from some notification class have an empty set image method, or some cash payment service extending from payment service throwing unspotted operation exception, or some interface implementation throwing runtime exception for unrelated functionality. All of these methods have one thing in common: they should not exist. These methods are trying to block functionality provided by their base class. They exist only as a result of bad inheritance hierarchy, which not only affects the readability of the code, but also affects the client code calling these methods. For example, from our first example, if a client code calls setImage method, then the client could expect that the SMS notification will also have an image in it, which is not true, and the client code will be disappointed. In this video, we will see how we can prevent all of this from happening in the first place by avoiding bad inheritance using the Liskov Substitution principle, or LSP. Liskov Substitution principle might seem like a title of some scientific research paper, but the idea behind it is fairly simple. It states that subclasses should be substitutable or can be used in place for their base classes. In other words, if you replace all base class objects with their child class objects, then the program should not break. But how does this simple thing help us avoid bad inheritance? Let's see an example. Let's say we have a used car base class in some car dealership management software. We have methods for common functionality like type, miles driven, registration details, engine specifications, and so on. Several classes are extending from this base class, like Toyota used car, Honda used car, Suzuki used car, etc. If we replace used car object with any of these classes, then nothing will break, since they all are subtypes. They all behave the same as the parent class and add their functionality on top of that. They are perfectly following the Liskov substitution principle. Now let's see what happens when we add Tesla to the scene. We create a subclass called Tesla used car, and there is a problem. Teslas don't have engines. So what should we do about getEngineSpecs method from the base class? Let's return null for now. Now we no longer can substitute a child class object for the parent class object. It will break our client code. Tesla used car class is violating LSP. Also, there is no way for the client to know this method will return null and their code will blow up. Sure, they can add special checks for Tesla, but tomorrow if Toyota, Honda or Suzuki introduce some sort of engineless car, then how we are going to deal with that? Not really an ideal solution. The real problem here is we have created a subclass called Tesla used car, but theoretically it is not a valid subtype of used car. To be a subtype, a child class must do everything a parent class does and add additional functionality on top of that. If a child needs to chop off parent functionality or alter the behavior of some method, like we are returning null engine specification for Tesla, then we are enforcing an unnatural parent-child relationship, which leads to violation of LSP, and we end up with bad inheritance hierarchies. To fix it, we can create another base class called electric used car and extend Tesla used car from it. Or we can reconsider the class hierarchy to accommodate electric cars. It is up to the team which solution they opt for. The Liskov Substitution principle helps us write better class hierarchies and also saves client code from getting into unexpected behaviors. I hope you like the video. If you do, please press that like button. Thanks for watching. See you in the next one.